It is my honor to introduce Simon Peyton Jones today for the first keynote of the Haskell Symposium. Simon probably doesn't need an introduction. I'll try anyway. Simon, since his time at Glasgow and then at Microsoft and now at Epic, has been the strength behind the GHC compiler that probably everybody here uses. He's also been a shepherd for this community, has helped us be better selves and better researchers. And again, it's an honor to be presenting, Simon. Please take it away and tell us everything about drawing points.
Okay, thank you. All right, thank you. Thank you for doing me the honor of coming. There is still a spare chair here. There's nothing wrong with it. It's a perfectly good chair. In the beginning, there was Rabbit. I was 20 years old when this paper came out. This is Guy Steele's thesis. Important part of his thesis was him saying, we should compile using continuation parsing style. Look at it, this was really very early 1978, the real meat of the compilation process. Continuation parsing style, a language isomorphic to scheme with the property to interpret it requires no control stack or unbounded temporary storage. The importance of these properties cannot be overemphasized. Well, I was sort of brought up on a diet of lambda the ultimate, so I thought, the real meat cannot be this is obviously the way to go. A little bit later, quite a lot later, actually it's 14 years later, Andrew Appel's book, Compiling with Continuations, came out. This is also a revelation. Andrew is also a deity in my firmament. And he's too said, don't use direct style in the compilation, just use CPS. Everything will be great. So by then I'd started to build GHC. And GHC was a direct style compiler, right? I sort of wrote papers about how it worked. So I was feeling quite embarrassed by now, right? All these famous people had been saying for years, use CPS style for your compilation. So why didn't I just adopt CPS style right away? Well, there were some reasons. You may think them good or bad, like CPS rather fixes the order of evaluation. That's part of the point. But in a compiler for a lazy language, you want to be a bit flexible about order of evaluation. You might want to float lets out or inwards, imposing an order of evaluation for everything. Not so good. And also, it's not really so good for certain kinds of transformation. Common sub-expression elimination isn't so easy. And inside GHC, we also wanted to do a lot of using rewrite rules to rewrite one term into another. And it's very convenient to have rules that say, f of g of x rewrites to h of x. By the time you encode this in CPS, it's not quite as easy for the compiler to spot that composition. Direct style is very convenient for that. So the reason for my embarrassment, therefore, was not entirely that I was lazy. It was that, well, of course, it was a lazy language, but that was it. Okay. So then, to my great relief, Cormac Flanagan and his colleagues wrote a paper that essentially said, you don't need CPS at all. Just use administrative normal form. I'm abbreviating this paper, which is a very interesting paper. So it's 1993 by now. So I breathed a sigh of relief and thought, fantastic. No need to use CPS after all. Andrew and Guy Steele were wrong. It's all fine, I just use A and F. But then, sadly, my very dear friend and colleague, Andrew Kennedy, treacherously betrayed me by producing this paper that said, no, A and F's no good. I mean, there's a lot of title engineering going on in the continuations world. Compiling with Continuations Continued, another nice title, don't you think? So, ICFP 2007. So he said, actually, there's juice that you can't get using the sort of Cormac Flanagan's A&F story. So the story of this talk, which is really from our paper in PLDI 2014, is, and I'll tell you how this collaboration came about, is to say, actually, this idea of join points that I'm going to tell you about today is the sort of, the power that says, no, Andrew Kennedy's wrong. We can actually do everything in direct style with the advantages that have, and not lose, I claim, anything or maybe anything much. There's going to be a challenge for you at the end to prove me wrong. Okay, so how did this paper came about? It came about at ICFP because Zeina Ariola approached me quietly and said, she sat down to lunch with me and said, Simon, you use the lambda calculus as your intermediate language for GHC, and you're very proud about it. You give talks about using, this nice small system F as an intermediate language. But she said that is the term language for a logic that is, it comes from natural deduction, right? It's the appropriate term language for natural deduction. She said, I spend my life thinking about sequent logic, and the natural calculus for that, the term language for that, is sequent calculus. So maybe sequent calculus would be a better intermediate language. So being a broad-minded fellow, I said, well, of course, Zaina, that could be. Let's see if we can understand it. And then I need to understand sequent calculus. And then I think, oh, man, there's lots of turnstiles and stuff happening to the left and stuff happening to the right. So it's a long period in which Zaina and Paul and Luke patiently educated me in what this sort of bottom row was. Luke, are you here? He is there in the corner, right. So Paul, sadly, is co-scheduled against this talk. He is giving a talk somewhere else. Right now, alas. Now then, so we sort of understood more or less what a sequent calculus intermediate language for GHC might look like, and Luke then implemented a parse in GHC that took core, this lambda calculus language, turned it into sequence calculus, then he optimized it, which is the bit that was going to be allegedly easier, and then turned it back into core again. That was quite a lot of work. And as it turned out, tell me if I'm misrepresenting, Luke. As it turned out, it was quite a lot of work and really wasn't better. Right? This, the sequent calculus, it had more data constructors in the language. There was quite a bit more hoo-ha to push things around, and we couldn't achieve any results. We couldn't achieve in direct style. So that was a little bit disappointing. Right? And so Luke had his hair falling out by then. Fortunately, it's regrown, I'm happy to say. By the way, let me say that this is a sort of tutorial kind of talk. It's really a bit of a retrospective, but I would love to have comments and questions as we go along rather than saving them up respectfully till the end. It would make me feel that you were actually listening rather than reading your email. So please do. Okay, so then having had this sort of slightly disappointing experience, we didn't give up. So Zaina and Luke and Paul and I had a lot of interaction. They very patiently helped me, and finally we emerged with this idea of modifying core in a very small way to add join points. And that turned, so it was a sort of like a principled extension in the end. And that's what I'm going to tell you about today. So the payoff is that we're going to get a small change to a direct style compiler that gives you access to all of the good things that we were hoping to get from the bottom line, okay? And it worked so well that when Ningning said, would I give this talk, I thought maybe, even though this is talking about stuff we originally published a paper about 8 years ago, thought if you're building a compiler of almost any kind in direct style, you really ought to know about join points. It's like a super useful, super easy thing. So that's my hope, is to just share the love today. Okay? All right. Now, so a little bit of background then. So which probably most of you know. So Haskell is a very, very big language. It has lots and lots of, its abstract syntax has lots of different constructors. So we type check that language and desugar it into this very small core language, and that's what we're going to be talking about today. And here is GHC's core language, more or less as it is today. And it really is quite small. I know I'm a biased witness, but I'm quite proud of the fact that 30 years on in GHC, it still only has variables, literals, applications, lambdas, let, case, type. What's type for? Type's for type arguments. It's a system F language, so you've got to have the argument of a function can be a type. And then classes and coercions I'm not going to talk about today. They're all to do with the new types and type families. Okay? So that's terms, which here are expers. What are types? Well, they're just type variables, literals, applications, type constructor applications, things like list of t. That's just arrow. And this is a for all type. So it's quite a small language. The coercion language is rather bigger, but we're not going to discuss it today. But also, in the optimizer, you never look at coercions. You build coercions. They're like proofs that you need to check that you haven't made a mistake. But the optimizer is never guided by the structure of a coercion. So the structure of this data type is not very interesting. We don't have lots of parses in GHC that look at the structure of coercions. Lots that look at the structure of expressions and look at the structure of types. And finally, this bind, this let here has a bind. What's in a bind? Either it's non-recursive or it's a recursive with a bunch of variable right-hand side pairs, okay? And every binder, like these IDs here, is, maybe that should be a var. It's ID is a synonym for var. It's just a pair of a name and a type, or if it's a type variable, a name and a kind, right? So every binder has its type with it. So that's it. That's it for core. And that's done us for 30 years, and it's still working quite well. Now, so that's the language we're going to use. I'm going to show you now a bit about the optimizations that we want to get access to using this join point stuff. So here is the place that I started, in 1990 when I was building GHC. Here's a function not null that's just not of null of x's, and I'd like to compile that, optimize it. So what is it? Well, so here's the definition of null and not. Right? They're just very simple expressions. One, null says, is the list empty, and not inverts a Boolean. So, so what have I done here? I've just inlined not, haven't I? All right, so case null of x's, that was easy enough. And now here I've inlined null. So now I've got a case, scrutinizing a case. Okay, so the outer case black, that's like a crocodile that's trying to eat the inner red case. And so what would I like to do? Well, really, I want to push that outer case to consume the arms of the inner case. So the outer case is still up here, so that I've just moved the same thing up. The black case, here, I've just moved it into the branches of the red case. This is really important that you understand this slide. It's not, there's nothing complicated going on here, but if you get lost here, you will be very lost in everything else, okay? So just tell me if you get lost. So here, what have I done? That outer black case, that's a copy of the black case that's scrutinizing that true, right, the first arm, and then I've copied the alternatives into the branch, and here I've copied the whole thing again, scrutinizing false. So far, so good? Easy? Yeah? Fine. So now, of course, I can simplify this case true, and I get, this is, of course, the code I wanted to get in the first place. I've just fused away the intermediate Boolean. All right? We have to do this. This is, the primary way that GHC optimizes things, to inline and then do lots of case and cancelling known constructors. Fine. It's not just case expressions that can consume these case expressions. It's also other strict contexts. Like, here's a case that's consumed by an application. Right? So here, you could think of that's a function applied to arg1 and arg2. So the application to arg1 and 2 is like the continuation. Oh, this outer black case, that's like the continuation, what to do after the inner red case. Here, these arg1 and arg2, I like to push them into the branches. And it happens the other way around. If you've got a strict function applied to a case, I might like to move that strict function inside and apply it to both branches. All right? So pretty much any strict evaluation context, we want to do this kind of thing on. Right. Now, there's a little worry that you might have that I've talked about duplicating stuff, and you might worry about duplicating arbitrary amounts of code. So here's, supposing the black case, the outer one, the outer crocodile, had big arms. Crocodile with big arms, right? Here, big 1 and big 2. Then I don't want to duplicate big 1 and big 2. This is slow my compiler down. So what can I do? What can I do? Let. Yeah, let. We could just let bind big 1 and big 2, right? That's what let is for. And now then I can jump to J1. It's a lazy language, so I didn't really need these units. But I thought there might be some call-by-value folk in the audience, so I thought I'd sort of try to avoid, making you sort of feel too uneasy. Okay, so this is pretty obvious thing to do, right? So we're going, but in order to make our continuation duplicable without blowing up code, we're just going to let bind these little J's. At the moment, they're little J's. I'm calling them join points, but they're just ordinary let bindings so far. Okay. Now then, the other, so having done that, now I do my case blah, 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 case blah, blah, blah. Now, look, when I've got to this point, J1 is called just once. So I can inline J1, right? However big it is, that's not code duplicative, but I sort of discover that later. So the first thing I do is I let bind it just in case. Then I simplify away, and then if it turns out it's only used once, I can inline again, right? So, fine. Now, the other point to make here, which is that the same idea generalizes completely smoothly to data constructors that bind terms, but bind term variables, or that bind existential types, or that bind GAD, or bind equality coercions. So here's an example that's just a term. So here now I've got a case in which I've got just X. And big one here mentions X. What should I do? Of course, all I have to do is to make J have X as a parameter. Simple. Right? And it will be fine if this data constructor had a type variable as its argument was binding an existential. That would be fine. I could pass that to J as well. Then J becomes a polymorphic function. No problem. This is system F. Okay? So this is one of these times. Sometimes you think, oh, here's a little problem, and it ought to be easy, but it's really hard. This time, there's a little problem, and it ought to be easy, and it is easy. That's always a relief. And on this occasion, it was. Fine. So then this is the next thing I'd really like you to remember. Probably all of you have spotted this, but these J's, I'm calling them join points because they behave like labels in a control flow graph. All right, so here's my little program here. Case X's, I take a case split, and then I take another case split, and then I go to J1 and J2. Why do I call it J? Because that's where you might join up or jump to, lots of J's here. So here, if you were writing it in a flow chart, you say, look at X's, look at E1, and then if E1 has one thing, I go to J2. And you can see that in terms of compilation too, you might imagine that I'm going to compile this into code that scrutinizes X, and then scrutinizes E1, and then literally jumps to the code for J1, passing X as an argument. Right? When I say jump to, J1 might have some free variables. This one does not have any free variables, but it might. But they'll be on the stack. So this jump amounts to adjust the stack pointer and go to. There's no allocation for J. Mostly, let, in GHC at least, allocates a closure in the heap. Join points, these we're going to have to be a bit more specific about what a join point is. These particular let bindings, they don't allocate anything at all. And the call to J here is literally two instructions. Well, sorry, put any arguments in the usual registers that you would for calling a function, adjust the stack pointer, and go to. Super efficient, no allocation. Yes? Hmm? Because it's a tail call. So these join points must be tail called. You can see the ones I've introduced had that property by construction. So yes, it's a very primitive sort of escape analysis, really, a particularly useful one. Okay? So this was the sort of key intuition. And in fact, in a completely unprincipled way, I'd had this intuition for ages. GHC, since its birth, spotted right in the back end. Did I write this out somewhere? Yes, right in the back end, GHC's code generator, if it saw the pattern of a let binding with some tail calls, it would not allocate for it. So as a sort of ad hoc, unprincipled, but useful optimization, it was called let no escape in those days. Often it had that. But in fact, then, subsequently I discovered that, all of this stuff has been known well since the very same Rabbit compiler. The same guy. This is earlier in the same thesis, and he disposes of it in 4 lines of text. Right, I'm devoting a whole talk, but Guy, very clever, he can do it in 4 lines. And here, look, if of if, so this is his case. If of if, he just duplicates the outer if into the inner branches. And he has the idea, of course, of avoiding code duplication using let binding. Right? Interestingly, though, this chapter of his thesis is before the CPS chapter. So he does this in direct style, interestingly. Okay. Now, so yes, so all good compilers and have been doing something like this, of course, for a long time. I don't know. I haven't managed to find out enough history about whether other compilers have done this GADT and coercion and arbitrary pattern thing. I suspect they have somewhere in reality. Not very much documented. So that was where we were, right? And then I met Zaina, right? And we got to figure out what to do because some of this is a bit ad hoc and principled. So the idea is that we're going to stick to join points as being some kind of let binding, but a little bit special. We're going to formalize what it means. This was the process that Luke and Paul and Zeno and I then went through. Then we're going to infer from, arbitrary code, some of those let bindings are already join points, by accident. Others we might introduce as part of this case-of-case swizzling business. They're going to be join points by construction. But others we might just find. And then we're going to teach the optimizer. So when I said this leaves money on the table, if we only do this stuff in the back end, which is all I was doing, we're leaving on the table some really good optimizations that I'm about to show you that we can do if in the optimizer we know that something is a join point, right? So not just the back end, do it in the main, repeatedly transform and simplify loop, exploiting join pointness. You better make sure that the optimizer doesn't lose any join points, right? Once having discovered a join point, you don't want to lose it. Because that would make the program less efficient. And then maybe there are even some new transformations that are altogether join point specific. And I'm going to show you all of those things, because since we wrote the original paper in 2017, there's been a kind of 8-year development, and join points have slowly, like the gray goo, they've slowly infected more and more of the compiler. We find, oh, look, if it's a join point, we can do something neat here. So they're becoming more pervasive, but more pervasive in a good way. They've offered new opportunities. They haven't generally offered new problems. So that's always a nice property to have. So I'm going to try to share with you not just the idea of what a join point is, but a bit of the sort of practical experience of using them in practice and what we've had to watch out for and what has turned out to be a new opportunity. Fine. So far, so good. Any questions or observations? Yes, please.
Yes. I thought part of the point was to solve the code duplication problem. Don't you still have the code duplication problem with your original example?
Let's go back to original example. Here. Can you repeat the question, Paul? Sorry, yes, I should repeat the question. Yes, so the question was like, don't we have the code duplication problem in the original program?
Well, we don't have code duplication, but we don't have the ability to, since we're not inlining here, we can't optimize away, we can't do that optimization where we flatten the two functions.
Oh, so the question is, if we do this join point splitting, like pull out the join points, do we lose optimization opportunities? Well, no, we get the one that we really wanted. The original one we wanted was, remember our original program back here. This was what we wanted, right? This case true of true, right? That was the one we were after. The outer case cancelling with the arm of the inner case. And we still get that, look. Look here. Here's big, big. The outer case, we don't, we make into join points the arms of the outer case, this guy, but not the outer case itself. So the outer case itself, this black case, it's duplicated, case true, false, case true, false. That's still duplicated. These J bits, they're not duplicated now. So of course, it might be that if you took big one and made a copy here and here, that you could somehow do something that you can't if it's not put there and there. And that might be an inlining decision. Perhaps the inliner can be clever about that. But to first approximation, we're getting the main payoff by duplicating the black case, but not by duplicating its arms. Okay? That's the idea.
Okay. Constant, you're duplicating a constant amount.
We're duplicating a constant amount of stuff, yes. Yeah. Anyone else? Yeah.
Excess, the parameters can lead to the inline. I mean, the inlining chances we may be losing, isn't it?
We may lose chances to inline because?
The parameter excess, I mean, if there's a parameter x that is passed to J1, I could have used that to...
yeah, this one here.
Right.
We passed J, yeah?
Right, so if I know the value of x in the case where I'm actually invoking J1x, I could be inlining it.
Oh, well, that's true. So you're saying that in here, if in this case here, I somehow get to know what x is, right, then I might call J1 applied to 3 and J1 applied to 7 in the other branch. And so now that's like if I've got a function definition and 2 calls to the function applied to known arguments, it might be a good idea to inline the function. Well, it might, But that's the same decision that applies to all functions, not just join points. So yes, that's a hard decision, but I love the way that it's the same decision for the functions that you write and the functions that are introduced by join points. So any heuristics or magic or flow graphs or everything we do will work for both. Yeah, it doesn't make it easy. It makes it the same hard. Anyone else? Okay, let's see. Right. So here in this paper, I'm not going to take you through the paper, but I do encourage you to read it. I was a subsidiary author, so I can talk it up. So here it described a little Lambda language, essentially the one I'm showing you, except that we added this join binding, join of JB. What's JB? It's a join binding, which just says it's either a non-recursive one or it's a recursive one. So it's just the same as before, like a non-recursive let or recursive let. But in this language, it has a different keyword. In the implementation in GHC, I'm going to show you, we don't use a different keyword. It's still ordinary let. And then jump, this is a call of the join point, a jump to the join point, like one of these guys here. J1 of P, J2 of P, in the little calculus of the paper, that would be written jump J1 of P, jump J2 of P, and so that's in the term language here. Okay? Yeah?
In GHC, jump is also, in GHC.
I think you switched it on now, it's fine. No, go ahead. It's on, yeah.
Yeah. So, in the GHC, does jump represented as like a normal application, or like
yes, inside GHC, a jump to J is represented normal apply, just a call of J. I'm going to show you a little bit more about that in a second. So I'm going to show you in a second how we map this onto GHC, but this was the language of the paper. So the language of the paper, having got this, we could then say, oh, and then here are some typing rules for the language of the paper. And you notice, I'll mention this later, but briefly, but J, these join point guys have a slightly funny types. They have type for all A something, a bunch of sigmas, arrow for all RR. That's a funny thing. So that looks a bit suspicious. It looks as if these join bindings bind variables that have weird types. So we're going to come back to that. And then there's an operational semantics that justifies the stuff I said about we don't do any allocation, and when we jump to a join point, we adjust the stack and jump. So look at this rule here. This is the operational semantics for a jump, and it says if on the stack I've got arbitrary stuff followed with a join that binds that J variable, then I just throw S prime away. I abort that chunk of the stack, adjust the stack pointer, and resume execution with the remainder of the stack, that little S guy. Right? Keeping the join bindings, though, because they might be recursive. Okay? So, again, I'm not going to go through all these rules. I just want to encourage you to believe that, with Zeno and Paul and Luke's guidance, we've got an operational model as well. Okay. All right. So, how do we map all this, which is really what this talk's supposed to be about, onto a real compiler? Well, it goes like this. A join point binding we're going to map not as a new kind of construct, a new data constructor in that core expression type, but rather just as an ordinary letrec binding. So in fact, inside GHC, the way it's tagged is the binder itself has a little tag on it to say, I'm a join ID. Right? You could imagine join IDs being drawn from a different alphabet, if you like. So in a let binding, these J's are drawn from a different alphabet. So I might write join J, but but all that means is that's let J, in which J comes from the join point alphabet, okay? And also, sometimes I usually write the binder on the left like this, but it's just ordinary lambda. So J equals lambda X. It's just the same lambda. It's not a special sort of construct at all. I should really have put, in this mapping thing, it would really be able to say J equals lambda X, dot right-hand side. Okay, anything else to say here? No? Okay. So, so that means that I said almost exactly like. What is exactly the same and what is different? It has the same representation, modulo this little tag on the binder of these binds to say I'm a join ID. It has the same semantics. This is very important, that if you take a core program and forget about the join point binders altogether, just turn them all back into ordinary let binders, everything runs the same. That's a good property, right? Because it means that you know what a program means. But it has slightly different operational behavior because a call, an apply of a join point binder is one is adjust the stack pointer. And also for lets, instead of allocating a closure, we don't allocate the closure, we just remember where on the stack to jump to, okay? So it is almost the same. The point that I think, yes, that's right, and making it the same as let bindings is a really big win. Right, why? Because, well, no need to add extra cases, that's one thing, right? So if you've got lots of GHC passes run over, deal with let expressions, mostly they can, to a first approximation, they can deal with join bindings the same as let bindings, like finding free variables, the same, right? Zero extra code, that's good. Inlining behavior, we were talking about that, right? With our colleague here, right? So inlining behavior, exactly the same rules apply for join points. Sometimes you think, maybe I could tweak it a bit. So there's room for tweaking, but to a first approximation, it's the same. Strictness analysis. Wow, this is a big deal in GHC, right? Or we're trying to figure out which functions are strict. If a join point is strict in an argument, we can do the same worker wrapper nonsense and so forth for join points as we do for ordinary bindings. That's really good, right? So not a whole new kind of thing. And also, as we'll see, there are some new opportunities we get. To first approximation, we can just use the old thing. But I do want to draw your attention to the fact that it's not quite what the paper says. So this, I don't think, is documented anywhere except in GHC's source code. So you heard it here for the first time. The thing that GHC implements is not quite what is in the paper. So look at this. Join JX. In the paper, you can write this. Join JX equals blah in case jump J3. In the paper, this is fine. What does this mean? This says, well, look, when I start to evaluate this case, as it were, operationally, you might imagine, I push a return address on the stack, and then I come to jump J3. What does that mean? Adjust the stack pointer and jump. So I'll throw that return address away. I'll abort that continuation. So as far as Zeno is concerned, Simon, what's the problem? Right? It's just the obvious thing. But this is not what ordinary let bindings do, right? If this was an ordinary let JX equals case J3, right, we'd literally call that function and return to the case, this abortion thing. In other words, the forget all about join points and it should mean the same thing would no longer hold. It was discomforting. It's, the join point bindings is no longer just an optimization, it's actually crucial. And moreover, I showed you briefly the funny type that join points have. That's a little awkward as well, and it's very convenient not to have funny types. If they're the same as let-rect bindings, no funny types, that was good. And moreover, this thing is completely useless. Right? What's the first thing we're going to do? We look at this and we say, case J3, we're going to always throw that case expression away, right? Just turn it into this. Throw it away statically at compile time. So we just arrange never to generate these kind of programs, just always to generate this one. So the extra generality had costs and it had no benefits. So in the implementation, it's a little bit less general than what's in the paper. But I found that was a compromise that worked really well. Yeah?
So does that mean that if the simplifier has something that transforms a program that already has join points into a form where the join point call is not in a tail position, then things are going to just go wrong? So
if the question is, if the simplifier sees a program in which the join point is not in a tail position, do things go wrong? Well, it's going to start with a program in which join points are always in a tail position, because that's the invariant, right? Now, what the simplifier arranges never to construct a program like this one. Yeah.
But if it did, then you would get problems.
Oh, if it did, then, so you might say, what if we made a mistake?
Yes, exactly.
Yeah, what if we made a mistake in some pass, and we took something that began life as a join point, and we turned it into something like this? That would be bad. But fortunately, where are we? Yes, fortunately, we can catch it rather easily. So the way that GHC's optimizer works is we run this little sequence of 3 passes a lot. And it works like this. Occurrence analysis is a bottom-up pass that finds how often each free variable occurs in the expression. Right? So the result of occurrence analysis is a little finite map from free variables to number of occurrences. Actually, it knows a bit about whether there's multiple occurrences in different branches of a case. But to a first approximation, how many occurrences? When we come to a binder, we say, oh, now I can see all the occurrences of that binder. It occurs 3 times. I'll tag that binder with the number of its occurrences. Maybe 0 times, maybe 1. That's helpful because then we can definitely inline it, maybe many, right? So Occurrence Analyzer, bottom-up pass that decorates the tree with occurrence information. Then the Simplifier does a lot of things. It does inlining, it does case of known constructor, it does constant folding, it does rule rewriting. It's a big smorgasbord of individual optimizations which are all smashed together into one pass. And then, and this is what I was to respond to your question, then optionally you can run lint. Lint is a type checker for core, right? So it checks that everything's type correct. It's system F, so it's fully type checkable. And in particular, it checks that everything that claims to be a join point is actually, in real life, a join point. So if you screw up and you, generate this, the next call of lint will blow up. Right? So if your Haskell program ever falls over with a mysterious compiler-ish error, always switch on lint. Lint is not on by default in production because, after all, if the compiler's correct, lint will always say yes. But if anything's gone wrong, you switch it on as your first debugging mechanism. Okay, yeah.
Hello. So in the paper you have an equational theory for join points.
Yes.
That really uses this explicit jump and, for example, also has an equation for throwing the continuation away.
Yes.
Do you still have a nice equational theory
without
the explicit jumps?
Yes, I'm going to show you. Okay. Yeah. So this is, in fact, this is a nice segue into what we're going to do next. Yes.
Are those join points just fancy tail calls?
Are the join points just fancy tail calls? Yes, I suppose. Yeah. It's just an ordinary let-rec binding with a particular property that, oh dear, I've forgotten. I've got a slide that lists the properties. Oh, here we are. It's the particular property that a join point has. If I've got a let, I might say of an existing let, is this let a join point? Well, I could say, oh, look, all of its occurrences are tail calls. None are captured in closures. They are all saturated. Yes, it's a join point. So the Occurrence Analyzer, as part of its work in doing this bottom-up pass, as well as now capturing how many times things occur, it also captures which things are tail called with how many arguments, so that it can tag all the binders with, is it a join point?
Yeah, see, so the tail call plus 2 more properties.
But, yeah, that's right, plus some more. It has to be, you have to be careful about the return type cannot mention any of the type parameters of that same function. So there's just a couple more properties, but yes. And so accidentally or coincidentally occurring join points are identified as such in each one of the Occurrence Analyzers, and thereafter we'll tell you if you ever screw up and lose it. So it's like a ratchet. You know, you get more and more join points and you never go backwards, right? If you ever lose one, then you get, lint will complain. Yeah?
Having join points as tail calls clearly is an efficient way, but if it is not a tail call, can it not still work? Because the way you explained it seemed to work either way.
Can a join point work if it's not a tail call? Here is something that is not a tail call. So in the paper, this does work, but in GHC, as I've explained, it does not. So in GHC, I've chosen a slightly less general form of what could be done, because it's a better fit with, I'm pretty confident it's a much better fit with everything else that's going on. That's what compiler design is all about, collections of compromises. This particular compromise, I think, is a really good one, because I think it has no costs and a lot of benefits. I like those kind of compromises. Anyone else? Okay, so, someone over here, sorry, yeah.
So actually, what's the advantage of the approach done in paper?
What is the advantage of the approach done in the paper?
Yeah.
Well, it's a bit more general, but as I say, I don't think it really has any advantages. Luke, do you agree? Yeah. Okay, so, I mean, as it were, the approach in the paper is a sort of what you get if you come at it from the, what's the sort of principle, you know, the sequent calculus hits the direct style join calculus, what's the most general outcome, and that was, that was the sort of synthesis, right? And then we just made it a bit more practical and found a way to do so without really losing anything important.
So it's, in a sense, it's just the most general or like a most natural way to come up with the calculus.
I think it's more natural to somebody like Xena, yes. But it wasn't more natural to somebody like me. I look at it and say, that's not a join point. Xena says, of course it is, Simon. No. Okay, so now let's talk about optimizing. So now, we talked about inferring join points. The Occurrence Analyzer infers the occurrence of join points. Yes, oh, sorry, go.
So there's two sources of join points, right? Some join point because they're introduced by case of case.
Yes.
Some start life as a normal binder and then inferred to be a join point.
Yes.
My question is, are recursive join points only ever coming from inferred join points, or is there situations where you would create a...
I'm going to talk about recursive join points, and indeed they are never constructed by this case-of-case thing. They only show up through inference. Okay. Yes. This what's called quantification in other papers. If you see quantification, sounds scary, but this is all it means. Actually, it looks a lot more complicated when you do it in CPS. Here it looks rather simple. Sorry, I couldn't resist a little dig. Okay, now, so now let's talk about the opportunities you get when you optimize a program that when you know that there are some join points in it already. Here is a transformation that is really good in general. Case of let x equal blah, 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 just ordinary let expression. It's a really good idea to float the let out. Why? Why is that? Why is it a good idea to pull the let outside here? Because? What was that? Common sub-expression? Yes, but there's something even closer to home. What might body be? Yeah. True, it might be a constructor. Yeah. What if body is a constructor, then I can do case true of, but if there's a let in the way, that's less obvious. So putting the let out of the way is very helpful. So forever GHC has floated lets out. That's clearly a good thing to do. But it's not such a good thing to do for joins. And it's bad so this is a slide which gives you, I think, some new information that it took me some while to absorb. So if there's a join point here, look, this join point is only called once, but never mind. The red guy is a little expression with a join point in it. If I float the join point out and then do the case-of-case transformation, I get this thing, right? Because now the branch of this is a JX. The black case goes in and scrutinizes the JX, case JX of true-false, and then case E2 of true-false, right? That's what would happen. Two bad things. Number one bad thing, J is no longer a join point. Look, it's not tail called anymore. Parche Zena. But even worse, the outer black, this black case here, is now scrutinizing JX. It's not scrutinizing E1. If you imagine inlining JX, so in that case it'd be just X arrow E1, well then the black case would scrutinize E1. We love cases that scrutinize E's rather than calls, because after all E1 might be true. Yes, might be true. So by abstracting out the J, that would be terrible, wouldn't it? So two very bad things. We've lost a join point, and we've lost and the join point has made things worse. Is that what the next slide says? Yes, the join point has made things worse. If I didn't have the join point, if I just had E1 there, I'd get better code. Abstracting it out, doing this business of sharing, it's back to what somebody at the back was saying. I've lost an opportunity by having abstracted. It was, yes, it was you at the back, Lyle, wasn't it? Yeah. By lifting out the join point, I've lost an opportunity to cancel this black case with E1. But what's the obvious thing to do? It's to exploit the, what we want to do then is to, well, look, we'd like to move this outer black case. Its business is to scrutinize E1. Look very carefully. Look, this outer black case, we'd like to duplicate it into the arms of the J, so case E1 here, and then in the red case here, this guy, instead of the J, I'd like to just call J prime and not have the black case. So the black case, the crocodile, has instead of the crocodile, instead of eating JX, has eaten JX's right-hand side. What a simple idea. Do you get it? Yeah, Jeremy.
You've been saying that join points are tail calls, but in the top example, J is not.
Sure it is. It's a tail call. Look, the binding here, if I'm evaluating this expression, then all I do is I have J, so I've got something, I've got my stack frames and everything. Then when I come to call J of X, I just adjust the stack pointer and jump. It's a tail call. It's a local tail call. I mean, of course, tail calls are always relative to some scope. Yeah. So at least for, never mind, we'll just define it. This is the definition, right? And You may not call it tail call. Let's call it wombat call. But wombat calls can be done efficiently, whether or not they're tail calls. Yeah.
Would it be correct to think about join points as if I install a reset around the join point and I replace an application with a shift into the applications?
Now we're getting into I don't know. So I once wrote a paper with Amar Sabri on delimited continuations, and at that point I'd sort of hash included just enough to think about chunks of stack, but I can never retain it enough. So I don't think I can give a meaningful answer, but maybe somebody else can. Jeremy, can you do? Maybe, okay. Anybody else? Okay, you're not going to give a meaningful answer. Anybody else want to give a meaningful answer to that question? But it's something to do with the kind of because there's something about, aborting a chunk of stack, which is very much like what happens with shift and delimited continuations, at least. Yes?
I think if you install a reset and you change the application to a shift, it doesn't change the semantics. I think that's what the join point is.
Okay.
Was the question on one-shot delimited continuation?
Oh, yes, these guys are one-shot. They can be recursive, though, in which case they can call themselves. We'll see in a sec. Yep. Okay. All right. So this part is important because this is the big insight that I finally learned that this is how we can exploit join points. If we know that it's a join point, we can do much better when we're optimizing code. Right. We're going to do this. We're going to push the continuation into the right-hand side of the join point. And this is the rule, coming back to the equational theory question, this is the rule from the paper. It says, here's an evaluation context. If an evaluation context scrutinizes a let, an ordinary let, then we just push the evaluation context into the body, right? But if an evaluation context scrutinizes a join, we duplicate the evaluation context into the right-hand side of the join and into the body. Don't you think that's beautiful? Oh, we've duplicated E, yes. But we know how to avoid duplicating E, right? What are we duplicating? The black crocodile. If R1 and R2, I mean, look, like here, this is what I said we should do. Of course, if R1 and R2 are big, we would just let bind them to be join points. It's turtles all the way down, right? Okay, so we can avoid duplication. Yes? Thank you. I'll show you a bit of code from GHC in a sec, and please ask your question again when you see some blue typewriter font. Okay. All right. So we're literally going to implement this this game about duplicating this continuation, and then the and this shows up directly in this code. I'm not showing you how I've done it, but the result of doing it is we've duplicated E. This E thing is the black guy, and he reappears here once in the right-hand side of the join point and once in the F, right? So it's very direct story. Now, and for jumps, what happens? E of jump is abort E, throw E away. Isn't that lovely? It's lovely throwing things away. And where did that happen? When we had this J here, we pushed the black crocodile around the J, and because he's a jump, he threw away the thing and just turned into a call to J, admittedly with a different type, as we'll see shortly. Okay? So it's very, very direct. Now, here to answer your question is, so GHC Simplifier is a pretty direct implementation of this evaluation context style evaluator. The simplifier takes an environment, an expression, and a continuation of some kind, and produces a new, it's in a monad, it produces some new expression. Now, so what's this continuation? Well, the continuation is, it's just a zipper. As we walk down the expression, we just stack things into the continuation. It's exactly a zipper for expressions. So cont is stop, or apply to, or select, and then there's a few more. And so here's the case for apply. Well, when I walk inside an apply, I'm going to simply evaluate, that should say fun, in a continuation in which I pushed arg onto the stack, right? The continuation stack, right? I've just walked down the zipper one stage. And for case, I'm going to push that onto the stack, right? Select is like a case with a hole in it. So this cont guy is precisely E. He's the evaluation context. And then, let's see. This is not I've oversimplified this because it is in a monad, and this wouldn't, I've written it as if it wasn't monadic. But for a, if I've got a join point, you know, if this is a join point ID, I simplify the right-hand side in cont and the body in cont. That's precisely doing this E duplication here and here, right? And now to answer your question, in the real code, of course, we've got to take cont and say, make it duplicatable, right? There's a call first that said, give me cont prime, which is a duplicable version of cont, plus possibly some bindings that must be wrapped around the result. So it's a simple and generic thing that happens in quite a few places. You know, one-off thing, take a cont to a duplicable cont plus some bindings. Yeah. Okay? All right.
Gist of that, you just go down one level in the AST and join point everything?
We go down one. Oh, yes. So you mean when we're making it duplicable? Well, remember, to make it duplicable, like we could take just one example. Maybe here's an apply to. If this is a big expression, then I don't want to duplicate that. So I'll let bind the big expression and make a small apply to that says apply to a variable, say, right? That's a simple thing to do. And you can do the same for these guys. And once you've done that, then if you make that duplicable again, well, they're already small, so we don't need to duplicate anymore. Yeah. Yeah. Over here.
If cont is E, then what is N?
Say that again?
If cont represents E, then what is N?
What is N?
What does env do? Like the first argument to simple.
Oh, env. Oh, this gives you, there's lots of stuff going on in env. It's like, because remember, we're also freshening variables, and if you've got a let bound variable, you need to know what it's bound to. So you can, there's lots of stuff in env. There's the, the mode flags of how much you're simplifying, lots of stuff. It's a big ball of wax. So, but have a look, this is fairly faithful to what GHC Simplifier really does. And I really like the fact it really does use evaluation context very directly as a data type. Okay. Just a quick remark is that when we push something into the right-hand side, of course, that may make the type of J change. Right, look, here's a join point J, and I'm going to push this continuation in. Well, this guy returns a char, but by the time I push the continuation into it, it's now returning a string. So it's not the same join point anymore. It's a guy with a different type. You just need to be careful to keep the types right. Okay. And that's also why we get a restriction on join point. Join points cannot have as their return type something that is locally bound in a for all here, because after all, here you might call it with int in both times. But if I push something into the right-hand side here, it would really be expecting to consume an int, because that's what both of these guys return. They both return an int. The continuation here is expecting an int, but it would find a right-hand side of type A. Not very good. So join points are not allowed to have this kind of type. That's a little type restriction on join points. Easy to enforce. But I'm not going to linger here. But this is the sort of reflection of when I say join points have funny types. They have perfectly ordinary types, but slightly restricted. Not any L value can be a join point. Okay. Right. Now, how long have we got? We got a total of 20 minutes from now. Is that right? Beg your pardon? 20, okay. So we have to speed up. Recursive join points. So I was delighted when I discovered that recursive join points just work. As Gergo said, this is only done by, they only occur when you infer them. So here's last, a recursive function that finds the last element of a list. Well, so its calls, possibly in its own body, are tail calls. And so we make it a join rec. Well, actually, it's just a let rec, in which last is marked as a join point. And then everything just works out. It's not allocated, you can jump to it, and it's recursive calls, it just jumps to itself. It's a nice type loop. It's very much like what people sometimes call loopification. Everything's very simple. The occurrence analyzer, discovering this, very straightforward. So it's another of those things, amazingly, that just worked out very nicely. And we discovered, unexpectedly, that we got some new fusion opportunities we never had before. So so here is a stream data type there's a whole little research cottage industry on streams. And just this look at this little guy here. This has a lambda s and then a let rec here with a recursive function that really is a join point here. That's good. And now filter, supposing you compose this filter S function with itself. So you'd like a filter stream function to somehow, you don't want it to produce an intermediate stream, you'd like those to fuse away. And while this is a let rec, it won't fuse away. But when it's a join rec, it turns out it does fuse away. And the details are in the paper. I'm not going to spend long on it. But the key step is that we end up with a case that's scrutinizing a join rec that looks like this, right? There's that step function in here. He turns into a join rec. And we end up, as you will be able to work out if you do the, the book work, we end up scrutinizing a join rec. Now, when we scrutinize a join rec, what happens? Well, we're just going to push this case into the right-hand side. And so this case blah ends up wrapping around this right-hand side, this right-hand side, and this right-hand side. So we get case done, case yield, and then a tail recursive call to step again, having aborted the continuation. Right? And look, now we've got a case of a known constructor, because blah is probably scrutinizing done and yield and so forth. So in effect, the continuation, which is scrutinizing the result of this is like that last function. It runs around a loop and finally returns something, and the continuation, the case blah, has zoomed in to the return branch when we finally exit. That's very nice. So in fact, we get beautiful fusion without any work at all. It's rather satisfactory. Okay. So much for those. Now, just a few other things that I found in experience reports from optimizing with join points. Here's an example with a let rec and a call to F that is not a tail call. So it's not a join point at all. But GHC, among other things, floats let inwards to be near their occurrence site. If you do that to this guy, look, we'll float that let rec, we'll go 1 plus let rec fx equal blah, 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 in fy. Now it's a join point. So moving functions, this doesn't always work, but floating lets inwards makes new opportunities for discovering join points. That was a nice discovery. It's not magic, but it's a good thing to happen. Inlining, super important, as I've remarked already. The inlining transformation already tries to say inline small things even if they occur many times, inline big things if they occur just once, so that happens automatically. And then what else might we do? We might need to be careful of, this is something we might need to teach the inliner that's new. Usually we're careful about inlining inside a lambda, right? This V, here's a func f of 22. Usually if we've got a lambda, we'd be careful about inlining into its body because the lambda might be called many times. But non-recursive join points are called once. They are one-shot lambdas, one-shot continuations, right? So this lambda is sort of special. We can definitely inline V into it. So teaching the inliner that join points can only be called once just by the virtue of being join points is easy and very effective. Another, even a trickier example that showed up, this I only did about 2 or 3 years ago, so relatively late in the game, is this. Suppose I've got this, not join point, just an ordinary let binding. There's a small expression here, and I scrutinize it several times. If I inline it, then several things might happen. The first thing, I might get case of known constructor and all of that. And also, here, I'm going to allocate a closure for small. Here, I won't allocate a closure for small. I'll just call it, right? If small was, factorial x, here I'd allocate a closure, a lazy thunk for factorial x. Here, I'll call factorial x. So less allocation, and also no allocation at all in this cold path. Well, this path that doesn't. Maybe this is the hot path, in which case I don't want to allocate small. So this kind of inlining can be quite effective in improving performance. But look at what happens if I made it into if it was a join point instead. So now what happens? I've got this V guy, but now V is really only evaluated once in the end. Look, on the A branch I call J, that evaluates V. On the B branch I call J, that evaluates V. On the C branch, V is evaluated here. On the D branch is not at all. So it would be safe to inline it at all three occurrences, just like before, right? But it's not so obvious because V is now occurring twice, right? Occurring twice. And it's no good saying, well, one is in a join point and one is not in a join point. If it was, it might be looked at on the way to the call of the join point. So we have to be careful here. So this was a place where for some while, GHC was behaving worse with join points because with this version, it would inline like crazy and good things would happen. And here it wouldn't inline and less good things would happen. Join points were making things worse. But what we have to do is just to be a bit cleverer in the occurrence analyzer and behave when J occurs as if you had inlined it. So the occurrence analyzer tries to behave just as if non-recursive join points were fully inlined. It doesn't actually do that. It just behaves as if and does occurrence analysis on that basis. That's enough. So that wasn't obvious to me. It might not have been obvious to you, but I'm now your experts. I hope it will be. There's a little wrinkle that was quite cheap to implement, well worth it. One other tricky corner. I'm still trying to show you tricky corners. This had me baffled for some time. Look, if I have this guy, this is the outer case. Oh, the outer case was usually black, but the crocodile has turned red. If the red crocodile eats this guy, I'm going to get case KFX. That's good, all right? Very good stuff. But, oh, this F guy is simply a free variable, right? He's defined in the enclosing scope. Perhaps he's bound to a lambda, a known lambda. So here, I end up with a call to a known lambda. Everything is good, right? I'm happy. But what if instead let's see, if I inline this join point, look, it's small. Surely I should inline this small thing. Let me inline it. It's 3 sites. So I get KF1, KF2, KF3. Now what happens? Oh, very bad. Now look carefully. The red crocodile scrutinizes, the right-hand sides, and beg your pardon. This might be big, so we're going to make a join point for him here called J1, J1GY, and then in the A case, we'll end up scrutinizing so that the case cancellation will still take place. We'll still KF1 of KGY, we'll call J1, and the same here and the same here. All right? And so we'll end up with this code. We'll call J1 of F, J1 of F, J1 of F3. Oh dear, this is very bad. See why? Why is it bad?
Indirect call.
It's a?
Indirect call.
Indirect call, that's right. Here, I'm calling this G function, which is passed to J1. I'll give the right answer, of course, but here I knew that F was this lambda. I could inline it and optimize more inlining could take place. Here, as it happens, G is always F. Right, some flow analysis might work that out, but I'd rather not make that mistake in the first place. So this is a little ad hoc-y. At the moment, we're just careful about if a join point right-hand side looks like a data constructor, I'm careful not to inline it. On the grounds the continuation will then see that data constructor. So I'm not very happy about this because it seems a bit more ad hoc and unprincipled. But inlining is an ad hoc and unprincipled transformation, really. GHC has a collection of not very satisfactory heuristics. A very few people, like Lionel and Celeste, have worked on improving GHC's inlining in general. I would love more research. Any research students here? I would love you to work on making inlining more principled and work better. Too ad hoc. Okay. 10 minutes ago? 5. 5. Okay. So then I'm going to skip exitification or exit floating. This is a transformation which you can. I'll leave the slides on my homepage somewhere. That is a transformation that identifies exit points of loops and pulls them out of join point right-hand sides. But I think I'm just going to skip this in the interest of time because I want to finish in a polite way. And here we are. In fact, this is the last slide. I like the fact that this is almost embarrassingly simple. I hope that everything I've shown you, you think, well, of course, right? Nothing hard here. That is the key to building compilers, is to find simple things. And so I think if you're building a direct style compiler, well, if you're building a CPS compiler, you might think of doing it in direct style after all. If you're building a direct style compiler, it's really worth paying attention to first-class join points because they're very simple to implement and they give really a lot of payload. And while you might want to make some more comments and ask some more questions, I'm going to leave you with a question is, tell me guys, you know, the things you can do in your CPS-based compilers that you can't somehow do using this, because I'm still on the lookout for those cases so that we can, I can understand better. Any other questions or observations from your own experience? Observations are absolutely fine, by the way, from your own experience. Yes, Robert.
If you go back to where we were talking about like the fusion for the stream filtering.
Yes, yes.
And we were like pulling the outer case into the branches, and in one of the branches we got rid of it because we were calling a join point. Isn't that I think
here.
earlier than this?
Yeah.
I think the slide after this. Yeah, here. So here in the jump step prime case, we get rid of the case that we floated in. Isn't that doing the thing that we said the paper did, and we don't do in the implementation? Where
No, that getting rid of the continuation around the jump is precisely the. Now we have to go back quite a ways. It's precisely right, this guy here. So the evaluation context, when it hits a jump, we throw away E and just leave the jump, right? And we really do implement that. That is not the bit that GHC does not do. GHC absolutely does this. And that shows up in the simplifier that when it comes across a call to a join point, right, it discards cont. Exactly as it looks like here, right? Except, I mean, it's not quite the same join point because it may have a different type, but you still get a jump with the same arguments. So,
wait, so where's the distinction between that and the thing that we don't do? Is it just that we don't allow it to be like explicitly written like that?
No, the distinction that we don't do is that in situations like, yes, here, this one, as far as GHC is concerned, this is not a join point at all.
Ah, okay.
Right, just isn't. Right, GHC's definition, no, not a join point. We never have to think of, so it's not marked as a join point. It doesn't enjoy any of these special properties, right? We just arrange that if you give me this program with a let, I won't infer it as being a join point at all. No, and indeed it isn't. But if you give me a program that does have join points, I won't ever construct this as a result of a transformation. So it's,
right, okay, thanks.
Yes,
Mike.
Are we done?
Yeah, we'll have a 5-minute layover, but it would be nice to unplug the computer. Trace can set up.
I can unplug the
question. We'll have 5 minutes. We can take a few more questions.
It seems that laziness saved you a few times in...
yes, hi.
Laziness saved you a few times where you could do some transformations based on the fact that you're in a lazy language.
I don't, can you give me an example? Because I don't think any of this depends on laziness.
I think there was one case where you lifted out a let somehow.
So I did say that when we create a join point, I could give it no arguments at all because I'm in a lazy language, but actually when it's a join point, even in a strict language, it wouldn't be something you'd evaluate call by value. A join point in a strict language, you just say, I'm not going to compile any code for that. I'm just going to adjust the stack and jump. So I think it's fine in a strict language as well. I think this is, my hypothesis is, everything I've said will work hunky-dory in a strict language.
All right.
I hope. If you find a counterexample, it'd be interesting to talk about it.
Yeah, one more. You go.
Yeah.
2003, I first heard you giving a keynote speech. 22 years down the line, you have gone 22 years younger. Thank you. I had one thing about the CPS where it's used. So we compile OpenMP programs, and we find that with CPS,
guys, can you be a bit quiet? I can hardly hear the question.
With one-shot continuations,
yes,
with CPS, right?
Yeah.
We are able to obtain wait and resume that is very difficult to do with natural style compilation. So with CPS, we are able to do wait and resume, which is amazing.
Wait and resume.
So we are mixing the two.
In a concurrent program?
In a concurrent program, yes.
Oh, a concurrent program.
Yes,
right.
That's a place where we are mixing both, and we are getting good.
Once you get concurrency, then continuations, of course, rear their heads in a different guise.
Just a bit to your question.
Yeah.
Thank you.
Okay. Concurrency. Yeah.
Very short.
I just feel like, I'm not sure if you're aware of continuation-based partial evaluation by Olivier Donvy and Julia Lewald, but I think they do something very similar. So basically, before that paper, people didn't know how to ether expand case statements. And ether expansion is really important for partial evaluation because you can shift cases in and out, depending to match it up. And I suspect that this is very similar to what joint points are doing in a way that I can't quite express.
Okay, well maybe you can figure that out, because of course I'm not saying continuations are necessary. Continuations are a whole field of wonderfulness, right? I'm just being sort of teasing you slightly about don't use CPS. There's lots to be had. So, but if you make that connection clearer, that would be great. Good.